Let's have a look at this idea of absolute value. Basically, the reason absolute value is important is because sometimes we're just interested in the size of the number and not the actual sign, whether it's negative or positive. So we have this idea of absolute value. The formal definition is this. The absolute value of A is equal to A if A is greater than or equal to 0, but it's equal to negative A if A is less than 0. So that way we always come up with a positive answer. What are we talking about? The way of thinking about it, if we think about our number line, is it's the distance from 0. How far away is the number we're talking about from 0? So as I say, it's magnitude only. We're only interested in the size. The direction, whether we're going in the positive direction or the negative direction, doesn't matter. Well, they give us this question, we say thank you very much. Absolute value of minus 5 then, of course, is just 5. Absolute value is a grouping symbol, just like parentheses. And if you remember your rules of operations, or order of operations, I should say, you always do what's in the grouping symbols first. So in this case, everything's in the grouping symbol. So 6 minus 8 minus 2 is minus 4. Absolute of minus 4 is 4. Again, we do what's ever inside the grouping symbol first. 6 times 3 minus 20 is negative 2, but the absolute value of negative 2 is 2, and 7 minus 2 is 5. Just like we see with algebra, we don't necessarily write the multiplication sign in front of the grouping symbol. So this is 3 times the absolute value of minus 6, so 3 6s are, of course, 18. All right. What about equations and inequations that involve absolute value? Well, this is where we go back to the definition. Remember we said it was equal to A if A is greater than 0, or is equal to minus A if A is less than 0. So there's two things this could equal, A or minus A, or in this case, X or minus X. So X could equal 7 or X equals minus 7. But when we look at equations and we start getting a bit more involved, we actually go back to that definition and write it that way. It's either the positive or the negative. So in this case, I say, well, the 2x minus 3 could be positive, so 2x minus 3 is 7, or the 2x minus 3 could be negative, rather than saying 2x minus 3 is either 7 or negative 7. Now the reason we do it this way, if we stick to the definition, when it comes to inequations, we're not going to muck up the inequality sign. Okay? More about that when we look at an inequation. So let's solve these. The first one gives me x equals 5 as a possibility. The second one gives me x equals negative 2. Absolute value equaling some algebra on the other side. It still doesn't change the way we do it. Either 2x plus 6 is equal to 3x minus 1, or the negative of 2x plus 6 is equal to 3x plus 1. Solve the left-hand side, we get x is 7. Solve the right-hand side, we get x equals negative 1. But here is where something that you've been told since you first started solving equations becomes very important. And it's something you usually ignore. And that is check your answers. Because if you have a look at x equals negative 1, if you sub it into the right-hand side of our equation, we will get negative 4. And so you're saying the absolute value of something is equal to negative 4, which of course is impossible. Absolute value has to be a positive amount. So actually, negative 1 is not a solution to this problem. So the only solution is x equals 7. So why does this happen? The reason it happens is because what we're solving is not the original equation. We have changed the original equation into something else to make it easier to find the answer. The original equation was absolute value of 2x plus 6 equals 3x minus 1, and we've said, oh, well, hang on, that's a bit tricky to solve, so I'm going to look at two different equations. Now, because I've created new equations, it's possible that I might create new solutions, which are solutions to the new equations, as in this one. X equals negative 1 certainly solves this new equation, but it is not a solution to the original equation. So that's why we always check our solution. Now, if you think about it logically, the only time this is going to happen is when you have absolute value is equal to some algebra. because that's the problem, isn't it? I subbed in -1 into the algebra and came up with a negative answer. If it was equal to a constant, like our second one there, equal to 7, it's not going to be an issue because the right-hand side is always 7. So this is the case where I really need to be careful with that. When I've got absolute value equals some algebraic statement. Okay. Well, let's have a look at an inequation. Again, I keep the same idea. Either x plus 5 is less than 2 or the negative of x plus 5 is less than 2. The first one gives me x is less than -3. The right-hand side gives me x is greater than -7. So I get the correct solutions. Had I done x plus 5 is less than plus or minus 2, I would have got an incorrect solution. Because in this second one, I would have said x plus 5 is less than minus 2. I've changed the sign, but I didn't change the inequality sign. So by always playing with the left-hand side, making that plus or minus, I don't have that issue. So that's why we always go back to the definition of what an absolute value is. The left-hand side is either a or minus a, we said, in that definition. And let's combine it. So we're saying x is less than -3, which would be all of those numbers to the left of -3. X is greater than -7, so therefore my overall solution is x is in between -7 and -3. Let's do one more. So either the left-hand side is positive, so 3x plus 2, or the left-hand side is negative, minus 3x plus 2. Solving the left-hand side, or the first one I should say, x is greater than or equal to -1/3. Solve the second possibility, x is less than or equal to -1. Let's plot those, see what I get. So, I tell you what, I've done something wrong, haven't I? Should have been coloured in those boundary points, because remember it's equal to as well in this case. So my final solution, although I did write it in my final solution, so x is less than or equal to -1, or x is greater than or equal to -1/3. What does an absolute value graph look like? So y equals the absolute value of a function. What happens? Well, we're never going to get a negative answer. So in my graph, whatever is below the x-axis must reflect above the x-axis. Okay? Whereas if it's function absolute value x, what we're saying is I'm only going to substitute in positive numbers into this function. I'm never going to substitute a negative number into the function. And what effect does that have? Well, that has the effect of the left-hand side of the number plane disappearing, because I'm never going to substitute in a negative number. But what's on the right-hand side then reflects over. Because when I substitute in -1, I'm actually going to substitute in the absolute value of -1. So I get the same answer as 1. When I substitute in -2, I'm actually substituting in the absolute value of -2, so I get the same answer as 2, and so on for every single x values. So whatever is on the right-hand side, or the positive side, reflects over into the left-hand side of the number plane. Well, this is the most basic absolute value curve there is. Y equals the absolute value of x. You probably know what it is straight away. But let's construct it. There it is. The classic V shape that we see. Now, when we are asked to draw y equals absolute value of x, I don't just draw the V shape. I need to put some sort of scale to it. So I'll plot in a couple of points. There's 1, 1, and on the other side, -1, -1. That gives it some scale. That probably does for our diagram. Another way people do it is sometimes they put a right angle there. And that's fine for this graph. But not all absolute value graphs are going to have a right angle. It all depends on the slope of the graph. So that'll only work with the right angle if, in fact, they are 90 degrees apart, which in this case they are. Well, what about the absolute value of x plus 2? I can think of it a couple of ways now. I can say, well, the basic curve is the absolute value of x. Okay. So I'll draw that in. But what have I done to my basic curve? In this case, the 2 is grouped with the x. It's inside the absolute value. So I have shifted it left 2 units. So that absolute value graph, whoop, there we go, over to the left 2 units. And so there is y equals the absolute value of x plus 2. Label a couple of points in there, as I say, to give it some scale. Well, that's one way I could think about that question. Another way I could have said was, no, actually, my basic curve is y equals x plus 2. And I'm going to find the absolute value of that graph. And what did we say that happens? If I find the absolute value of that graph, whatever is below will be reflected above. Bingo. And we get the same shape. So it doesn't matter which way I think about it, I come up with the same answer. Absolute value of x plus 2. So I could think of it as saying, hey, the basic curve is y equals the absolute value of x, but this time it's not grouped with the x, it's grouped with the y. So I've shifted the whole thing up 2. There we go. Or I could think of it as saying, no. Again, the basic curve is y equals x plus 2, but this time it's only the x I'm finding the absolute value of. So this is function absolute value of x. And what we said there was anything on the left-hand side disappears, and then we reflect the right-hand side over. And so again, we get the same graph. Y equals the absolute value of x plus 2. There's no reason why it has to be a straight line. We can get some very interesting shapes. Y equals the absolute value of x squared minus 2. Well, that's the basic parabola there of y equals x squared minus 2. If I find the absolute value of that, we say, well, okay, whatever is below will reflect above. And we get like a W for that particular graph. So that would be y equals the absolute value of x squared minus 2. Now, I'm not suggesting that you would use a graph to solve this inequality, or inequation, I should say. I would solve this algebraically. However, had I already drawn the graph and had it handy, then I could use it to solve it. So there's my absolute value of x plus 5 graph. We're saying, when is this graph less than 2? So I could draw in the line y equals 2, and I'm saying, hey, when is this graph below my red line, y equals 2? So I know I'm in between 2 points. I'm only interested in the x values. Question is, what are those 2 points? So I could go and solve the equation to find out, oh yes, it's minus 7, 2 and minus 3, 2. But again, I'm only interested in the x values for this. And so there's my solution. X is in between minus 7 and minus 3. As I say, probably not the first technique I would use for that question, but had I already drawn the graph, well then maybe it's a useful way of doing it. All right.